Hello and welcome to our broadcast today titled Why, When, and How to Use DOAS, brought to you by the experts at Renew Air. I'm your host today, Tyler Kern. Thank you so much for joining me. I do want to let you know that we want to make sure that you're getting all the information that you need from this broadcast today. So with that being the case, there's a comment section down in the bottom right-hand corner of your screen. And if you have any questions or comments throughout the broadcast, make sure you drop us a comment there and we'll try to get back to you as soon as possible with an answer to your question or a response to your comment. So be aware of that comment section down there in the bottom right hand corner of your screen. So now let me introduce our experts who are going to be educating us on all things DOAS today. First and foremost, we have Nick Agopian. He's the VP of Sales and Marketing at Renew Air. Nick, thanks so much for joining us.
Thank you, Tyler. Great to be here. Appreciate it. And thank you for hosting this as well as the other delegates.
Absolutely, absolutely. Thank you so much for being here, Nick. And we also have Alex Smith, Regional Sales Director at Renew Air. Alex, thank you so much for being here as well.
My pleasure. Thank you, Tyler.
Certainly, certainly. And last but not least, we have Rich Gerby. He's the co-founder and CEO of Highmark Group, LLC. Rich, thanks so much for being here.
Hey, hello, everyone. It's my absolute pleasure, and thank you to Renew Air for inviting me. Appreciate it.
So that is our panel of experts we're going to be hearing from today. So Nick, you're going to kick us off today. Give us an introduction to ventilation and indoor air quality, and talk us through how DOAS plays a role in that.
Absolutely. Ventilation is something that doesn't necessarily have the spotlight as other mechanical systems in buildings, and typically ventilation previously has just been looked at as a table in a code document, and depending on the activity indoors, you just select a CFM per person and you run with it. However, what people don't realize is ventilation is critical on how the physiological operation of the human body functions and its efficiency in that function within the built environment. And ventilation, as I may have said earlier, it has been around for millions of years. Early humans realized that if they were able to ventilate a space, they could bring fire indoors. Egyptian stone carvers performed more efficiently when they carved outside and there was air that pulled away some of the stone dust rather than carving the stone inside the pyramids themselves. So ventilation has been around for millions of years and aids us on how we live inside the built environment. Now, if we go back to the 1900s, we used somewhere in the range of about 55 different products for construction. Today, we're over 50,000 products that are used inside the built environment. And the main reason for that is because of the oil embargo back in the 1980s, where we had to save energy, and buildings consume close to about 70% of the total plugged load here in North America. Out of that 70% of the total plugged load of a building or a home, ventilation itself is about 50 to as much as 70% of that plugged load. So there's a high energy cost when it comes to ventilation. And what we did is we looked at sealing these structures tighter and tighter by using these additional tens of thousands of products, but to make it more energy efficient. And the second we did that, we ended up with something called sick building syndrome, or deficient indoor air quality. Ventilation has been increasing in the volume that's being introduced per person ever since that problem in the early 80s. So ventilation is critical on how human life lives indoors and is perceived indoors.
Well, Nick, what a great point. And given where we are today with all that's going on in 2020, indoor air quality is really now in the forefront of so many people's minds, whether it be schools, whether it be office buildings or transit centers and airplanes, where now people are really starting to understand the importance of indoor air quality. And, as a design professional here in New York City, we're seeing this and being asked about this all the time. And, what a great way and a great position to be in, to have DOAS technologies here in place and available to us as design professionals. And I'll tell you, the design community is very excited about a lot of the DOAS products that we're seeing out there today. And a lot of the advancements that we've seen from companies like Renewair. So it's a very exciting time, and it's exciting because we can help tackle, this problem of indoor air quality and diluting a lot of the impurities and from a lot of our industrial process, a lot of from carpets and desks, right? All of those things that are hurting our cognitive function. Now we've got this COVID situation, and what we're seeing is now we've got this virus that's around us that, boy, how important it is to really take care of our indoor air and to create these environments that are safe for building occupants.
Yeah, I think that's a really a great comment, Rich. It's interesting to me how, you mentioned furniture and carpets and fixtures and fittings that off-gas VOCs, volatile organic compounds like formaldehyde and so forth. It's interesting how the pandemic has kind of brought the issue of indoor air quality into sharp relief, but it's always been around. I mean, indoor air in private residences and commercial buildings is routinely 3-4 times more polluted than outdoor air, and in some cases up to 100 times more polluted than outdoor air. So the pandemic has certainly brought it into sharp relief, but there has always been that issue, and that has meant that ventilation dilution has always been an important factor. People just haven't sort of warmed up to it as much until now.
Yeah, we've certainly come a long way. If you think about early engineering designs and how we used to design buildings, I mean, as near as 15, 20 years ago, we were designing systems that were constant volume systems or overhead VAV systems that were basically anywhere between 50 and 20% outdoor air. And there was really no importance or impetus put in how we were delivering that outdoor air into the space, and whether we were actually providing enough. We were designing these systems where at peak operation we were putting anywhere between 15 to 20%. It was a nominal number, didn't necessarily correspond to what was going on indoors. And the other side of that was there was really no impetus or really any thought was going into how that air was being delivered to the unit, and from a temperature and humidity perspective. So a lot of challenges there. And again, and that's kind of another thing that we're seeing now is the importance of controlling humidity inside of these spaces. I mean, we're talking about that, and healthcare professionals are looking at that as being a indicator and a possible, helping to aid in the spread of COVID in a lot of these buildings.
Yeah, exactly. The whole purpose of indoor air quality focused designs were offering a way to be able to control how our body functions. And of course, some of those were reversible issues, some of them are irreversible issues. But when you do bring in the COVID question, now it's no longer just indoor air quality for better health, but now it's all about safety. It's all about safety and protecting someone indoors. And cognizant authorities like ASHRAE, like the CDC, like we have in Europe, and the DOE and the EPA and OAS, and we can just continue through an entire list, is that minimum ventilation as advocated by code is a start point. It's not necessarily what is considered a high performing building. And when we look at the control of the spread of something like COVID-19, we have to increase the amount of outdoor air that's recommended by code to become a high performing building. So is that 30% above that? Is it 100% above that? Or is it a 100% outdoor air system? And as I alluded earlier, when we're taking a look at the energy profile of a building, 70% of it can come from, or is from the HVAC system, and 50 to 75% of that 70% is conditioning the outdoor air. So when we look at energy recovery in a DOAS product, we're able to optimize the energy profile of a building because we're recovering the energy from the exhaust air, And then more importantly, we're decoupling the, I guess, the energy conditioning between what is in the outdoor air and what is on the indoor air. So a DOAS product becomes paramount in the design of a holistic energy profile of a building, and optimizing that energy profile based on that minimum demand or that increased demand that I'm alluding to. And without a DOAS product, it's going to become extremely expensive to operate as compared to when you do have a DOAS product.
Nick, just to piggyback that thought, I mean, and I love you saying that, because to me, DOAS without energy recovery is a tremendous disservice to, a building owner, as a designer, not designing a system with, not considering DOAS to have energy recovery, to me is it's such a problem. I mean, for the sake of running some duct work and getting that outside air. When you think about, especially like a building in New York, where I'm located, the amount of exhaust that comes out of these buildings, and the temperature and the consistency at which we take air out of these buildings, there's so much energy in it. And, from a sensible and from a latent perspective. And, it's just a matter of running a duct and connecting those two airstreams. And what's great about the Renew Air product is, with designing it correctly, we could be at 0% cross-contamination. So a lot of the concerns and a lot of the air that historically we had to exhaust because the perception was maybe it had an odor in it, maybe it was coming from a place that we didn't want to put it through, certain technologies because there could be a transmittance from one airstream to the other. I think a lot of people shied away from energy recovery in DOAS because of that. But now, it's really a no-brainer. I mean, thinking about what DOAS systems alone did for indoor air quality, in terms of, the buildings, the energy models did prove that decoupling that ventilation did drop energy consumption in the building. The other side of that was it gave you significantly tighter control of the air temperature and humidity coming into the space. Now combine that, right, with energy recovery, and the savings are significant. And the savings are to the point where where we can go back and now start to over-ventilate buildings, as Nick had said. And we know that there's a clear benefit. Designing a building for minimum outdoor air, is kind of what we, are recommended to do. But looking at that in terms of, let's look at all these positive advantages that we could potentially have now. And we can do that because the energy recovery allows us to do that without there being any energy penalty. No increased building tonnage, no increased heating loads. So we can increase ventilation and still net less energy. That's an absolute great thing.
Yes, I think there's a misconception on a DOAS product that's almost like a commodity in the market as compared to a DOAS product with energy recovery. And a lot of people don't understand the financial metric that could be used against energy recovery. Besides the typical payback of less than 3 years, in some cases even like a little over a year, there are other metrics like internal rate of return and net present value of future cash flows. And with like something like an NPV, net present value of future cash flows, then what happens is that anything that's a positive means that it's a good investment. Well, when you run these financial metrics, you find that you're 200, 300% above what would be considered, yes, a good investment. Or if you're looking at internal rate of return, you're seeing internal rate of return of 120, 130%. Where do you get that? Not even in the stock market can you get that these days. So energy recovery ventilation using a DOAS product is definitely the most economical way of doing it, because as you alluded to, the energy has been put into that air to temper it when you first brought it in. So why not recover it? Why throw it out? Why send it back into the environment when you know that there's a positive way of doing it with zero cross contamination, which makes it extremely safe and healthy.
So Alex, we got a really good introduction into DOAS there and got into a lot of the different topics about DOAS that we're going to cover today, but we know that these systems aren't designed the same way as traditional systems, right? So walk us through some of the major differences, and then when and what are the ideal situations in which DOAS should be used?
Yeah, good question. Well, Nick has discussed the indoor air quality ventilation situation. And what we're really talking about here is introducing high amounts of outdoor air, high percentage outdoor air to maintain a minimum ventilation dilution rate. So that's become prescriptive for both health and safety reasons. The problem with that is that, as you can imagine, in many parts of the country, the outdoor air during the summer months gets very hot, very humid. I'm thinking the Gulf Coast, Eastern Seaboard, many places in the US where it gets very hot and very humid. It stands to reason that you cannot bring that outdoor air into a space for the purposes of ventilation and not treat it. If you didn't treat it, everybody's going to get miserably uncomfortable very quickly. And added to which, if you are bringing in outdoor air for the purposes of ventilation to dilute the space and get rid of volatile organic compounds and things like that, you introduce humid air, and then you immediately set up. It's the problem that you're replacing creates another problem, because very humid air can set up amplification sites in certain places for mold and mold growth. So, you cure one thing and you start another. So you have to have some kind of treatment to the outside air. And that creates a problem for conventional equipment, because most HVAC systems are not designed, never were designed to condition large percentage outdoor air. As a matter of fact, with the sort of prescription for increased ventilation, most of these systems now find themselves having to condition as much as 70% outdoor air, and when they were only ever conceived to do maybe 20%. So this is a real problem for conventional equipment. Most of the time, they're doing recirculation. That is, they are conditioning the air, which is simply recirculating through the space. So this added load on them places enormous energy drain on them, and they never ever are able to condition and meet the space conditions that we need to stay comfortable. And that's been reflected in the standards as it relates to the equipment up to now. There has been a situation where, because conventional equipment has not been designed to do this, they have had no standards to lay down benchmarks of performance and efficiency. And as a result of that, what's happened in the industry is that in many instances, there's been cases where the wrong standards have been applied to that equipment. So, for example, with conventional equipment, you have energy efficiency ratios and these things have been related to cooling and heating capacity, not for dehumidification, which is one of the primary functions of a dedicated outdoor air system. So the standards that have been applied have been what's known as ASHRAE 340, 360. They have not been appropriate for dedicated outdoor air systems. There is now AHR 920, which actually is a new standard in recent years anyway, that sets out a benchmark for how you measure a dedicated outdoor air system. And it talks about moisture removal capacity, moisture removal efficiency. And these are metrics that are specific to it being treated more like a dehumidification piece of equipment rather than conventional heating and cooling equipment. And that's important because the definition of a dedicated outdoor air system is that it must dehumidify 100% outdoor air. It may or may not use energy recovery, preferably with energy recovery, as Nick and Rich alluded to. But at the same time, it must meet the minimum ventilation requirement that we've been talking about to maintain this dilution rate and keep everybody healthy in the building. And so that all leads on to the primary differences, which are performance. We've now got this piece of equipment which is designed from the outset to cool and dehumidify high percentage outdoor air. And there are many instances where you would adopt that approach. For example, high occupancy density. So we're talking about multifamily dwellings, assisted and independent living type applications. Schools, these are institutional type applications, schools and colleges where there's a lot of people. Anywhere where there is a high volume of people that requires a high amount of ventilation air. And there are also applications where the internal environment is really pretty nasty. So we're talking about recreational things like cigar bars. Obviously, you've got a high level of smoke and nicotine in those spaces. They all need to be adequately ventilated, otherwise that's not going to work. You've got situations like hospitals and waiting rooms. Waiting rooms are actually notorious for volatile organic compounds and germs, because people sitting in a waiting room nursing some kind of injury or a physical problem, there's a lot more germs being spread in a waiting room than there is actually in a surgical suite, which is inherently sterile. So these are all kinds of environs where you would adopt a DOAS approach to ventilate these types of spaces. And I guess that the finale to this is the actual performance of the unit versus the performance of the conventional equipment, because the dedicated outdoor air system must now supply that ventilation air, dehumidified, cooled, but down to a very low dew point, or a lower dew point than conventional equipment would be able to do. So there's a fundamental difference in the capability and the design of what the unit's actually supposed to do. This is probably the biggest key difference as it relates to the difference between the two pieces of equipment and how and when they should be used.
You mentioned regulations and codes and things like that. Is that something that is consistently being updated, and do states have different regulations and codes that manufacturers need to be aware of and things along those lines?
Well, states, the answer to that question is interesting, that many states adopt, or the mechanical codes that they adopt in different states are generally taken from ASHRAE standards. Usually they're a few years behind, and the mechanical code that the states adopt aren't necessarily verbatim what the standards say. So they can be modified and amended. And moreover, some states will actually cede authority to a local, to a city or a local municipality. So there can be differences as you go from state to state and city to city. But generally speaking, the codes that are adopted are based upon ASHRAE standards. Now, ASHRAE itself, as I mentioned earlier, has not had a standard, certainly no efficiency standards with regards to dedicated outdoor air systems, certainly not until about 2013. In 2013, AHR I-920 came into being, and for the first time we actually had a standard that related specific to dedicated outdoor air systems. And as I mentioned before, they get treated more like a specialized dehumidifier than they do conventional cooling and heating for regular equipment. So the standard for DOAS is fairly new, and it's still not widely adopted in many cases. I still see codes or standards being applied that aren't really relevant to it. So it takes people some time to catch up to. But I do anticipate that as we go forward, then those will be those standard AHRI 920 standard will probably be modified and updated as we go forward over the coming years. Yeah.
The codes themselves, depending on the climate zone you may be in, when you compare a very cold and dry area like Minneapolis as compared to Miami, that has a different design strategy because it's very hot and humid. But Alex touched on something which is very critical, and that word dehumidification is vastly misunderstood. A lot of times people look at a system, and if you've got condensate coming out of it, means that you're dehumidifying, but you're not controlling your humidity level or the dew point that you should be controlling at. And a DOAS system, if I was to compare it to a car, a central station compared to a DOAS, a central station would be like a big super tanker in the ocean trying to make a turn. In the ocean, it'll probably take you close to about 5 miles to be able to make that thing turn. As compared to a DOAS is more like a speedboat where you can just do a quick turn. These climatic conditions, and to give you that relationship, you can have a situation where it's cool and wet in the morning, and then it starts to heat up and it becomes hot and humid by noontime, and then it becomes very hot and drier as you get to the late afternoon. And these systems have to be able to immediately change its operating design point to be able to suit what's needed in order to dehumidify or cool that outdoor air to the conditions that are needed indoors. And we know that by dehumidifying, we're able to make it more comfortable for the individual indoors. So that feeling of better well-being when you have a drier and warmer air as compared to, you're feeling humid and you're feeling sweaty. So what's the first thing people do? They turn down the thermostat, and suddenly they end up with a condition of maybe 69 degrees and 75% relative humidity. And it becomes very humid indoors, where a DOAS can dehumidify and make it more comfortable for the individual, offering maybe a 40% relative humidity condition. And rather being at 69, you could be actually up at 78 if you wanted to. And that would be better for your body. And I know that the Arthritis Association came up with a position statement where they were saying having a warmer and dehumidified environment is better for your body than having a cooler and more humid environment for your body. So dehumidification becomes very critical. And I don't know, Alex, if you could touch on the mistakes that people make not understanding what it means to design for a peak wet bulb condition or dehumidification condition as compared to where inherently all designers go to peak sensible instead of the other one.
Yeah, that's a really important point because many designs are based around peak wet bulb, and what that means is that in the hottest summer months, the temperature in dry bulb and wet bulb is not necessarily the highest humidity time of the year. And in Rich's area, for example, in New York, yes, it gets up to 90 something degrees in the summer, but the hottest, wettest day of the year is not then. It's actually more like when it's 83 degrees temperature and the wet bulb is 71 degrees. And if you're going to design a DOAS unit to dehumidify, you must design it based upon the hottest, wettest, or peak wet bulb design day. Now that may only occur for a minimal number of hours in a year, but you still need to design for it, because if you do not, and you design, say, for example, for peak dry bulb, what will happen is when the dedicated outdoor air system is faced with that high humidity day at 83, 71, What it will not do is be able to dehumidify that load down to a leaving condition that you're looking to supply into the space. In other words, your cooling coil will be short on capacity. So you must design for the hottest, wettest part of the day, even if it is only for a few bin hours per year. And so that's a critical thing. And I do see on a lot of schedules still to this day, many DOAS units that are based upon peak dry bulb, which is not the accurate way to do it. The second thing that I would say is that very often you will see a design condition, a leaving condition from the DOAS unit of 55 degrees into the space. 55-degree dew point. The problem with that is that a 55-degree dew point into the space equates approximately to about 62 grains per pound in moisture. If you're looking to maintain the room condition set point at, say, 75 degrees and 50% relative humidity, that corresponds to a grain load of around about 67 grains per pound. So the difference between the grains of what you put in and what you're trying to, or the return, what you're trying to control the space at, is very small. And it is that difference which gives you your dehumidification capacity. So it stands to reason, if you've not got very much difference between the two, you're not going to get very much dehumidification capacity. So one of the things that a DOAS unit has to do is to be able to dehumidify to a lower dew point of that. So if, for example, you dehumidify down to a 52-degree dew point and you supply that into the space, now that corresponds to something more like 57 grains. So now you've got a much bigger delta between the grains in and the grains out that actually gives you some dehumidification capacity. And there are formulas for calculating the airflow and the load and what the grain delta needs to be in order for you to dehumidify all of the outdoor latent load and all of the indoor latent load. And it's a common mistake and probably the biggest difference in terms of performance criteria between a DOAS unit and a conventional HVAC unit.
Excellent. I'll just add one quick point that in an improper design system that allows a higher humidity condition indoors promotes microbial growth, which many people don't realize, but the metabolic function of microbials actually generates VOCs. And VOCs with ozone generates a submicron particle less than PM 2.5. And PM 2.5, we know, can adversely affect how our heart works, our cardiovascular works, and more importantly, how our brain works. And PM 2.5 is suspect to being a contributor to heart attacks and strokes, and is being right now researched as a promoter or an instigator to Alzheimer's in the brain. So it's really interesting because a simple design or lack thereof can cause a lot of problems indoors. And I am sure that everybody here on the panel and our listeners have been to a southern hotel where you go in and you have that musty smell. Well, those are microbials. That comes from an improperly designed system to handle that dehumidification load. So it becomes very critical.
And Nick, if I can just add one thing, from a field experience perspective, I appreciate you guys bringing this stuff up because, you know, and this is kind of talks through the history of how DOAS kind of went, right? When we used to bring air directly to a air handler, you know, dehumidification worked pretty well. The challenge there was we didn't have very tight air temperature control. And in the old days, you know, if you go back to being an old enough designer, they put a big reheat coil. So, you know, you would drive the leaving air temperature down, get all the moisture out of it, and then reheat it back up. And that was just an energy code nightmare. So when we stopped with reheat, all of a sudden we had all of these humidity concerns and all these humidity issues. And to your guys' point, lower temperatures, we were satisfying the space from a sensibles perspective, but we were doing absolutely nothing to drive out that humidity.
Yeah.
I think where that got even compounded, that problem, was when we started to go to terminal DX equipment and fan coil units. And fan coil units, when we were supplying outside air directly to a fan coil, it wasn't a great thing because we were not, what we were finding in our experience here in New York was when we were able to dehumidify the air enough, we weren't getting the condensate out of the air handlers. And what would eventually happen is we would re-evaporate that, because we would have a situation where our sensible temperature would be satisfied and we would stop cooling. Our cooling coil would no longer be cold. And all of that work that we did, we would just re-evaporate that humidity back into the air. So we never took the moisture out of the drain pans. We couldn't physically get it out of it. And that was an issue with the VRF systems. That was an issue with water source heat pump, terminal water source heat pumps, and fan coil units. So, you know, I think, and I liken the DOAS systems as being this precision device that provides a very precise entering air condition, or, you know, a outdoor air, or I should say outdoor air at a very specific condition, a controlled sensible and a controlled latent. And what's great about it is, like Alex said, hey, you got to design it to the right starting point, but a DOAS system is going to control it the right way the whole time. And it's going to basically have the controls in place to supply that air as efficient as possible at the right temperature. And you know, honestly, from an indoor air quality perspective, we talk about humidity as being an indoor air quality concern. DOAS systems have addressed all of those issues that we had historically. And, you know, like to Nick's point, when you go into a building that doesn't have a DOAS system, or it's just dumping outside air into a space, or maybe they're going directly to a terminal with outside air, a terminal cooling device, boy, you know it right away, because it is cold and it is clammy. But, you know, a system that's got a properly designed outdoor air and it's giving you that consistent temperature, it, you know, A, it's going to reduce your energy consumption, and, you know, but B, boy, that indoor air quality is going to be, you know, you're off at such a great starting off point. So a very good point, and I appreciate you guys bringing that up.
Yeah, you're right about some of these systems, these very highly efficient VRF type systems, or chilled beams or radiant panels. They do not have any dehumidification capability. It has to be done at the DOAS, and if you don't do it at the DOAS, you're spot on. You're going to end up in a very uncomfortable situation and an unpleasant experience for people inside that structure. Great point.
Yeah, the sort of conclusion to that, specific to your question, Tyler, is that if you have a DOAS unit which dehumidifies a high percentage of outdoor air and cools at the same time, and it takes all of that load onto itself, those conventional systems that we were discussing earlier that were never designed to do that, whether it's a VRF, as Rich and Nick were just saying, or fan coil units, or whatever it is, these local cooling devices in the space that were not designed to dehumidify are now freed from that. They don't have to worry about that anymore. All they have to do is do sensible only cooling, which is what they're predominantly designed to do. There is a small amount of dehumidification that goes with that, but mostly the load is mitigated and they can do what they are designed to do best, and that's just do the local cooling. So they can do recirculation, because now they've got their big brother, the DOAS unit, handling everything else. So it makes for a much more efficient approach, rather than trying to make a terminal unit, like Nick just said, you know, these, whether it's evaporator coils in a VRF system, or whether it's chilled beams or fan, but it doesn't matter what they are, they're predominantly sensible cooling devices, and now they can get on with doing what they do best.
All right, so at this point we've talked about the why for DOAS, and we've talked about when, and also a little bit about some of the critical differentiators for DOAS versus traditional systems. So now let's talk about the how. Rich, lead us into implementation and talk to us a little bit more about that process and what that looks like.
Absolutely. Yeah, as anything else, with designing buildings, there's always great engineering questions that have to be asked and answered. And I think one of them that we always look at is, and we always kind of have to look at things from a vertical market perspective, from a how are we designing the space perspective. So there's never a one size fits all answer. I always preface this and start the conversation by saying we're going to do what's best for the project and recommend, a system that's going to solve as many of the issues as possible, understanding that there's been a number, typically when we come to the table to talk about DOAS, there's already been a number of decisions made as to how that building is going to be built. I'll talk about a couple of the applications and types of systems and basically would be the conversation that we would have coming in after a building owner, a design engineer has made a decision on what type of system to ultimately use. But what I would start off by saying is most of the systems that we are designing today are direct to zone systems. It definitely has become very popular and definitely something that we weren't able to do years ago before the kind of the widespread adoption of DOAS. And the reason for that was because nobody wanted to put a duct directly from the outside of the building to the inside of the space. If you think about it, what was ultimately happening in those issues was if that air did not go through an air handling unit, it did not go through some H&V unit, that air would basically go into the space cold and dry in the wintertime and hot and moist in the summertime. And the reality of the situation is, when we think about a building with a traditional kind of ceiling and you've got air coming in, air coming out of vents, that you've got a conditioned airstream and you've got this unconditioned airstream, they would be on a crash course collision and would create huge thermal comfort issues inside of the building. What's great about DOAS systems is essentially we're designing these systems, and the way that the physics works and the psychrometrics of these systems works we are able to deliver air very close to the temperature that we're controlling the spaces to. And because of that, we can go directly to the zone. Which is a great energy saving, a great money saving, saves us in terms of ductwork, it saves us in terms of complexity. When I think about going into an old building in New York City with a 15,000 CFM unit and monstrous ductwork running from the space back to the space, exhaust fans in the space, economizer ductwork, all of those crazy things, so much of that is simplified now. I think about the office that I built here in New York City. We built a raised air plenum where we do underfloor air distribution. And with that, we've got Renew Air Energy Recovery, basically diluting all of the pollutants. We've made the decision, we're ventilating at about 60% over the ventilation rate that's recommended for our building and what it was designed to. And what's great about that is we're doing that with zero energy penalty. We're actually able to increase our outside air to significantly higher than what was recommended, and do that again without it costing us any money to operate the system. And because we've decoupled it and because we're going direct to the space, we're also able to save on a tremendous amount of ductwork. So kind of a really cool design there. And when you think about the VRF systems that are being done, when you're thinking about even a rooftop unit, just being able to go directly to the zone, like for instance, in out in the suburbs, we have office towers that are anywhere between 3 to 4, 5, 6 stories tall. We're able to basically now put DX rooftop equipment on those spaces. And historically, DX rooftop units were not great at dehumidifying air because the reality of the situation was if they were not in cooling mode, they were not dehumidifying. So, and the fans were always running constant. So again, if we didn't have a cold coil, we were not dehumidifying. Now, what's great about these energy recovery systems we can have our standalone unit, which is essentially taking care of all of the sensible load from people and solar and, internal processes, computers and such, and the internal humidity load inside of that piece of equipment, decouple that, and now have a DOAS unit that is providing us very precise air into that space. And again, we're providing it at a temperature and humidity level that we can pour it directly into the space, and it has zero impact on the temperature control or humidity level of that space. Like Alex said, we're providing it drier. So it actually is working essentially to help us in a lot of instances when it comes to a humidity perspective. And then again, conversely, in the wintertime, we're providing it at a temperature and we are humidifying it when we're utilizing a Renewair energy core so that that air is not too dry, that we're providing the important humidity levels that we're looking to do there. So again, it's a great way for us to supply outdoor air directly into the spaces. I think one of the secondary benefits of this is the fact that we can now build significantly tighter buildings. Because, I think, again, back to when I started off as a designer in this business 25 years ago, one of the things that every building had was a floor-by-floor air handling unit system with huge holes in the side of the building. And that was where we were bringing in air in and out of them. And if you went into those buildings back in the day and stood at the top of an air shaft or an elevator shaft, the amount of stack that we were getting through those buildings, there's always going to be a natural convection of air moving through a building. But because we had these holes and these buildings were not tight, there was so much, it was almost impossible for us to control the air going in and out. So forget the temperature, forget humidity, the physical quantity of air that was going into the space, we had no idea. VAV systems made that even harder because now we were speeding fans up, slowing fans down. Energy, now talking about economizers, made it even harder to figure out all of this stuff. Dedicated outdoor air systems supplied, directly to the space makes it significantly easier for us to tighten up these buildings and for us to ensure that we're getting the air in and out of them. When you think about like a passive house application, which would be, typically a smaller size unit, boy, it is, so increasingly, important nowadays. And we've seen just in home building alone, where we tightened up all these buildings and all of a sudden we had all these humidity concerns. And we were having all the mold growing in rafters and stuff like that because we weren't able to ventilate these buildings. Now we've got this great system of, well, yeah, we want to keep these buildings tight because we don't want infiltration because that's a cost to energy. But what we do want to do is we need, and it is imperative for us to properly ventilate these spaces. So, what we're looking at is in a lot of times as we talk about these terminal systems, whether it be a fan coil system, a water source heat pump building, which is a very popular system in New York. It's a DX system that typically are, you're putting one of these in a room by room type of basis. It's kind of the same logic as almost a larger package rooftop unit in terms of the humidity issues. But I definitely would say, those type of systems and the challenges that we have there is that they're not good at taking care of outside air. What's great about these DOAS systems are now, like in the case of, I think a great use case is we talk about multifamily residential, which is a very big thing here in New York and actually across the entire United States now, right? What we're able to do is provide the ventilation into the spaces and directly from a centralized location. And that ensures that those people are getting the ventilation that they need, as well as that, again, it is as a precise humidity and temperature as possible. And there's just so much benefit there.
Yeah, no, it's I can endorse what you're saying, Rich. More and more I see applications moving towards direct to space rather than feeding some downstream unit. And I see it all the time, whether it's in hotels, hotel corridors, or reception areas in office buildings, and it's all direct into the zone. And I see that more and more.
And it's great because, like, for instance, when in the time that we've been Highmark here in New York City, I mean, we're seeing the prevalence of DOAS systems. I think our business is almost doubling in terms of the opportunity of DOAS year over year. And there's just so many reasons for that. And it's really lending, and it's an exciting thing. And I think now that what we're seeing is, there's this comfort level with going direct to zone that so many people are okay with this. It brings the cost down considerably, and and just the indoor air quality benefit and the energy benefit of the operational energy benefit is just significantly higher. One of the things I'd like to add though too, and a credit to Renew Air, is their course program has some great capabilities and allows us to really analyze and make decisions on what the correct and proper sizing should be on these systems. It used to kind of be that old 55 was the magic number, right? We supply air at 55 and it always worked. Well, that's not the case necessarily anymore. And I think when we start to look at the DOAS systems shift our mindset from a temperature to a dew point temperature control, as opposed to just a pure sensible control. And kudos to you guys, because you've got some great design tools that help the designers. And I know a lot of my engineers here in New York support the consulting engineering field, and we use those tools to help our engineers make some really educated guesses. And it's a great tool to have.
Well, guys, we've covered a lot of ground here today and talked a lot about the DOAS system. And so, Nick, I want to turn it back over to you just to give us any final thoughts, if you want to summarize the benefits of DOAS as well, and then tell us where we can find more information.
So I want to thank everybody who contributed with all of the content that we listened to today. We realize that construction has made the buildings much tighter, whether they're homes or office buildings or schools or restaurants, it doesn't matter. We are now living in a structure that's so hermetically sealed that our activities indoors has a detrimental effect on how we interact with the space. We know that not only activity today, where because of COVID, we're using a lot more ammonias and a lot more chlorines, and while we may not smell them inside the space, they are there and they do have a detrimental effect. Alex was right earlier when he alluded to 2 to 5 times as much as 100 times more dirtier indoors than the outdoors. And that's because there's a cognitive dissonance where we come indoors in the middle of January in Minneapolis and we feel it's heated and we're protected. Conversely, in Miami in July, we come indoors and we feel that it's cooler than the outside, so we're protected and we feel it's better. But Alex is right, it's not better, it's a lot worse. And even gases that we emit as human beings, such as carbon dioxide, has a negative impact. And that comes from research from NASA and Harvard and Lawrence Berkeley, showing that there is a detrimental effect to cognitive decision-making abilities. But more importantly, CO2 is an acid and adversely affects the acidity in our blood, which attacks bone marrow, and that's irreversible. So when we look at the codes and standards out there that are being written, they're following things like DALY, which is Disability Adjusted Life Year. And they look at many different reasons why we end up living with I guess people with COPD, or we end up with living in a life in our later years, which is not as efficient in our younger years when we had more energy and so on and so forth, and then die young. And when we look at smoking, high body mass index, high blood pressure, and so on and so forth, out of 75 reasons why we live with disability and die young, 2 of the top 10 reasons is because of indoor air quality. So we're looking at ventilation numbers today compared to the world. And what we realize is we have the lowest level of ventilation inside spaces compared to everybody else in the world, which is absolutely detrimental. We know that we can control the spread of COVID by increased ventilation. We know that increased ventilation, all in all, is better for us than if we don't. The only way we can achieve that is, of course, to use a DOAS type product. And we learned that you can't just design a DOAS and just put it in based on certain conventional design strategies where we have to look at alternate design strategies, such as what Alex said, where the dehumidification peak is critical, or else what we thought was going to be the solution in using a DOAS product ends up being part of the problem because our humidity levels are too high. So the design and the application and the operation to what Rich was alluding to becomes very critical on a successful installation and operation in order to improve indoor air quality. And we know from some research that came out this past year from Lawrence Berkeley, where the study conclusion said, overall, the number of reported statistically significant improvements in health with increased ventilation rates far exceeded the anticipated chance of improvements in health. What does that mean? That means if you design the correct ventilation and increased ventilation to be considered a high-performing building with the correct energy recovery and correct DOAS that's designed and applied correctly, have a better chance of improving your health than if you tried to take vitamins or tried to go to the gym. I'm not saying you shouldn't go to the gym, but improper ventilation and improper design of these systems will negatively impact your health. So please come visit us at renewair.com. Our course selection program that Rich alluded to absolutely will help you to be able to achieve everything that we discussed today. So thank you for your time. Thanks, Alex. Thanks, Rich. And appreciate, Tyler, for everything you've done to help us to get to this point.
Thank you so much, Nick. And remember to head to renewair.com for more information. And Rich, what's the website for Highmark as well?
You can always come check us out at www.highmark.co.
There you go. That's the website for Highmark as well. So everyone, thank you so much for joining us for this broadcast today. We appreciate you joining us. Remember, you can drop us a comment or a question there in the comment section, and we'll try to answer as many of those as we can. And we appreciate you watching along with us, and stay tuned for more. But until then, I've been your host today, Tyler Kern. Thanks for watching.